First, okay. By Davide Ravotti, Ergodic and mixed properties of Horocycle flows and their time changes, a temporal distributional limit theorem.
Thank you very much. So I want to start from where we stopped last time. So last time, recall we were studying the ergodic integrals for Horocycle flows, and we managed to prove rather strong result about the speed of convergence. Namely, we found asymptotic. I can actually go back a few slides. So we found a nice asymptotic expansion. So recall this was denoting the ergodic average of the function f at the point p up to time t, and we found all asymptotics for the convergence of the ergodic averages to the expected value. One thing we can also ask is try to make some other statements. So one thing you could do is think of the ergodic averages, or even better, the ergodic integrals as random variables, and ask yourself, can I center them and normalize them so that I have a non-trivial limit in distributions? In the limit, I think of ergodic integrals as random variable, and I see in the limit some interesting non-trivial limiting distributions. So the question is, how do we see our ergodic integrals as random variables? And historically, what people do is randomize the starting point. So you have an invariant measure. Now you take the point randomly, the starting point t randomly with respect to this invariant measure. You look at your family of ergodic integrals, you think of them as a family of random variables. Can I center them and normalize them so that in the limit I have a non-trivial limiting distribution? And for other dynamical systems that are more chaotic, so for example, for the geodesic flow, in the same setting as we are, but for the geodesic flow, one, if tries to do this, sees a central limit theorem. So if you randomize your starting point, take your ergodic integrals up to time t, under some assumption on the function f that you are integrating. Once you center them by the expected value, t times the expected value, you normalize by the square root of t, you see a normal distribution in the limit. And so you can ask, can I do something similar for the Horocycle flow? And you can prove in some cases, in many cases, not all, but in many cases, you can prove some distributional limit theorems. And what is interesting is that contrary to the geodesic case, the limiting distributions actually will be the distribution in some case of, they will be related to the distribution of these functions that recall all they're continuous. They are continuous in particular, and the space is compact. So they have a maximum and minimum. So the limiting distribution will be compactly supported. So they will be non-trivial, but yet compactly supported. So this is a interesting feature of Horocycle flow, but I think more in general, parabolic systems that have a non-trivial limiting distribution of Weber non-alpha. But I don't want to talk about this. I want to talk about another way, another class of distributional limit theorems where you still look at the ergodic integrals, think of them as random variables, but instead of randomizing the point, now you consider the point as given as a deterministic datum, and you randomize the time. And the question is, can we do the same? So can we center this family of random variables, normalize them, and find an interesting limited distribution? So before giving you the statement, I will work our way to it. So I will talk about a temporal distributional limit theorem. So hopefully now that these words make sense. So I want to focus on the case mu equals 0. So recall mu was the eigenvalue of the Casimir operator. So now I will limit myself to this case. So I will consider a function f that is at least, say, C2 on my space M, and I will assume that is in the kernel of the Casimir operator. So when I do the Casimir, I get 0. Okay, so what can...
Sorry, yes, I was absent. So could you remind is the Casimir.
Yes, so I definitely have it backwards. I don't remember if I have it forward. So let me go back. Okay, I have it here. So the Casimir operator is we defined it some time ago, so maybe it was good to recall it. It's a second-order differential operator. So it takes, say, a C2 function and gives you back a continuous function, and it's given as a sum of three second derivatives. So this R denotes the derivative in the direction of the rotation subgroup. This X denotes the derivative in the direction of the geodesic. And this Y denotes the derivative in the so-called orthogonal geodesic flow. So it's associated to the matrix Y given by 0, 1, 1, 0.
So hyperbolic.
This, if you exponentiate, would be hyperbolic cosine, hyperbolic sine. And I think geometrically you can think of it as rotating by pi over 2, I never remember in which direction, follow the geodesic and rotating again. So it's the orthogonal geodesic flow. So this is this operator. You take this linear combination of second derivatives. And we proved in the first lecture it has the nice property that commutes with the dynamics and with all other differential of first order differential operators given by elements in the Lie algebra. So for and we also, well, okay, in this case it's not very. So we also proved that if your function, or we sketched that if your function is invariant by this subgroup, so if it's constant on SO2 orbits, this means that basically it's a function defined on SZ1 modulo SO2 that was isomorphic to the hyperbolic plane. This operator coincides with the minus the hyperbolic Laplacian.
I see.
Okay, so now, of course, if f is invariant by SO2, this would be the hyperbolic Laplacian, and you only have constants here. But there are other functions that are not SO2 invariant that satisfy this condition. But for the moment, let me just assume that they exist and we want to study them. So, in order to study our ergodic integrals, last time we defined our function j, and we proved that it satisfied a linear ODE with constant coefficients that was given by j double prime plus j prime plus mu times j equal e to the minus t of g. So now I'm assuming that mu is equal to 0, so the constant, the term mu times j disappears, and this is the ODE that I had. And recall that this was then related to the ergodic averages of Horocycle flows. Okay, so this we can solve it in the same way as we did for the other cases. So the solutions, well, they will consist of two terms. Each of the terms is associated to one of the roots of the characteristic polynomial of this equation, which is x squared plus x. So the two roots are 0 and minus 1. And indeed, in the solution, you have a constant term that corresponds to the 0 root and a term that is like e to the minus t. That makes sense? Okay, so my function j, by solving this ODE, it's a constant term that will also depend on the initial condition, but for the moment I'm ignoring them. This term that is e to the minus t times an integral from 0 to t of my function g that was explicit, and I will recall it in a second, plus something that is a big O of e to the minus t, so it's smaller. What is this constant? Well, remember that this function j was related to the ergodic integrals, the ergodic averages for the Horocycle flow. So j at time t was related to the ergodic averages at exponential time e to the t, and you also had to change the point, the initial point. But we remember, as John will show us this week, that the horocycle flow is unique. Yes?
Is part of the geodesic flow?
Yes, this is the geodesic flow, yes. Yes, this is the geodesic flow at time t, and here is exponential. The horocycle flow is uniquely ergodic. This means that the ergodic averages converge uniformly in the point to the integral of the function. So if I assume that my function has also zero integral, then I know that uniformly in the initial point in here, the ergodic averages will converge to zero. Therefore, the function jf in subnorm at time t will converge to zero uniformly. Does this make sense? So the constant here has to be zero because this goes to zero, this goes to zero. This is a constant, but we know it has to go to zero, so this constant has to be zero. If we assume that the function has zero average. Okay, so we found an expression for jt is this term here plus something that is O of e to the minus t. And I'm gonna expand what the g was that we found in the previous lecture. I'm gonna expand what the g is and recall that the ergodic average at time t is j at time log t. Okay, so there will be some log appearing. So if I unpack the definition of j and g that we saw the other times, we can prove the following theorem. That is another case of what we did last time, essentially, but I want to spell it out. So if f is a C2 function with zero average and such that is in the kernel of the Casimir operator, then for any point in time, I have my integral for horocycle of the function f along a horocycle orbit equal to this term on the right. So let's spend 1 second to look at this term on the right because it's telling us something quite interesting. So here on the left-hand side, I have the ergodic integrals along the horocycle orbit. Here on the right-hand side, I have an integral where this time the variable is on this term here and this term here, which are the geodesic flow. So what I have done is I managed to relate the ergodic integrals along the horocycle orbit up to time t with the difference of two ergodic integrals up to time log t along the geodesic flow. This is the key observation. Okay, so it's an integral along the geodesic flow starting at point ht of p minus the integral along the geodesic starting at the point p. So if I recall that if we draw an image, so if here I have the point P and here I have my horocycle orbit up to time t, then I can also look at what happens along, so this is my horocycle orbit and these are my geodesic orbit. And recall that we had the commutation relation that was taking long orbits of horocycle flow into very short ones up to an exponential contraction. So here I have the point pi x of time log t of p, and here I have a short horocycle orbit of length 1. And this formula here is related to this picture here. So I related the integral along this orbit of time t with the difference along these two orbits of the geodesic flow of a different function, the function bf, plus a constant term that essentially would also be given by closing this quadrilateral over here. Does this make some sense? Okay. So we continue by looking at this formula over here. And okay, so here the extrema of integration is log t, but I can actually, so if instead of stopping up to time log t, I continue, these 2 points here are a distance at most 1 because this horocycle orbit segment is at length 1. If I continue, they become even more and more close together. They become exponentially, like they converge exponentially fast. So the extrema here being log t is not really, it's not really important. So if I notice that if you integrate from log t to infinity the same object, so if you continue these two orbits and integrate what you have here, you have a constant, and most a constant, because the distance becomes exponentially small. Therefore, I can replace in my formula before the extrema log of small t with another term, log of capital T, where capital T is going to be larger than little t. You might ask me why you are doing that, but it will become clear in a moment. So up to a constant term that has changed from the previous line, my ergodic integrals up to little t is the difference of these two integrals along the geodesic orbit up to a time log t, where log t is going to be larger than log little t. Yes.
So do you play this game on the compact situation or on this whole space?
On the compact. On the compact. Yes.
Otherwise, it's not true, or it doesn't matter.
What is not true?
Okay, the statement about this approximation of Horocycle by this integral way difference.
Yeah, no, it's, I need it. Well, yeah, definitely. Probably it's not going to be true in the, yes. I mean, just replacing this extreme integration, if the function is not too bad, it's going to be true, but the step before, yeah, no, I need some.
And it only works in the case when mu is equal to 0. Otherwise,
you don't have this equality if mu is not 0. Okay, so we are up to here. Okay, so let me rearrange this formula again. So let me call this the integral of this second term here. Let me call it capital C T of P. So it's something that depends on capital T and depends on the initial point. It's the integral of this function up to time log T. And I will take it on the left-hand side of the formula. And then I will divide everything by the square root of log T. So I take this term, put it on this side, and divide by the square root of log T. So this is my ergodic integrals up to little t minus some constant that depends on the point and on the capital T. I divide by square root of log capital T, and I'm left with the 1 over square root of log T, and then this integral. Plus, so this was a constant, now I'm divided by the square root of log T. This is some term that goes to 0. Okay? So what have we found? We found this, I've just rewritten here. So again, let us look at it, and I want to convince you that this formula will tell us a temporal distributional limit theorem. I will not prove it, I just want to give you a hint of why this is true. Okay, so now recall to prove a temporal central limit theorem, what we want to do is now take the time randomly, uniformly in some interval 0 capital T. I will take it in some interval 1 capital T. It's not really a problem. Randomly, uniformly. So capital T now is going to be fixed. And imagine that I take little t randomly in between 1 and capital T. What is in the left-hand side? I have my random variable. So this is random, the randomness coming from the choice of little t. I subtract a constant that depends on capital T and T, so this is deterministic. And I'm normalizing by this factor the square root of log T. If I prove that this converges in distributions to something, I prove the temporal distributional limit theorem. What do I have on the right-hand side? In the right-hand side, I have an integral of some function Bf along the geodesic flow. So here I'm integrating along the geodesic flow, where if I chosen, so P was fixed, and now I choose little t randomly in between 0 and capital T. So I'm choosing a point randomly uniformly along a Horocycle orbit of length capital T. So now imagine this being capital T, and I'm taking little t somewhere uniformly along the orbit. Okay? So this point at which I do my ergodic integrals for the geodesic flow is random because the randomness comes from this little t, chosen randomly uniformly. And now is the part that I'm gonna hand wave. But so the Horocycle flow is uniquely ergodic. This means that if you take the measure uniform on a Horocycle orbit segment of length capital T, and you let t go to infinity, this measure will converge weakly to the volume measure. This is the definition of unique ergodicity, basically. So I hope you believe me that, or at least it makes sense that, okay, now I'm taking a point randomly uniformly with respect to a measure that is supported, is uniform on a horocycle orbit segment. But this measure, when t becomes larger and larger, will converge weakly to the volume measure. So it's not maybe too surprising or too unthinkable that instead of thinking this as the measure distributed randomly on a horocycle orbit segment of length t from p, I can think of this point chosen randomly uniformly with respect to the volume measure. And so on the right-hand side, I have a normalized ergodic integral for the geodesic flow where the point is picked randomly uniformly with respect to the volume measure. And for the geodesic flow, we know it satisfies the central limit theorem. So can we apply it? And the answer is yes. So this is a non-proof, what I told you, but it can be turned into a real proof. And you can prove the following temporal distributional limit theorem for the horocycle flow. So this theorem was proved originally by Dolgopiatt and Sarig in 2017. And Emilio Corso wrote an appendix to the paper I was talking about by myself, and he deduced from, as I was presenting you in this slide, this result from the formulas we saw last time and today. So the statement again, if f is a C2 function with zero average and in the kernel of the Casimir operator, okay, I have to assume something to make sure that I can use the central limit theorem for the geodesic flow. So I will assume that f is not a measurable coboundary for the horocycle flow. This will be enough to allow me to apply the CLT for the geodesic flow. Then there exists some positive sigma such that for every initial point, if you look at the ergodic integrals up to a time that is picked randomly uniformly between 1 and capital T, you subtract this constant that will depend on the point, okay? And of course on capital T, but not on little t. You normalize by the square root of t, and in distribution, you converge to the normal distribution with mean zero and variance sigma. So this is the one instance of this temporal distributional limit theorem, and in this case, it's particularly nice that you can deduce it from the spatial central limit theorem for the geodesic flow. I think other questions on yes.
It gives you nothing about
sorry.
It gives you nothing about central limit theorem for horocycle. So temporal and usual are completely independent.
Yes, correct. Yes. Yeah, they are two different. So the classical spatial limit theorem tells you of the distribution up to time t. Yeah. The temporal limit theorem, you fix a point and tells you the whole history. So yeah,
but someone would think that okay, so the statements are different, but nevertheless maybe something differ behind, and some guy implies another or something like that. But probably it's not true.
I do not see immediate. I do not see a connection, but it's not true. I mean, it doesn't mean anything. I just don't see it. So yeah, yeah. Change of slides. Okay, thank you. So now we start talking. So we talked about ergodicity for the horocycle flow. So now we talk about mixing properties of horocycle flows. And I want to prove mixing, and in particular, I want to prove quantitative results of mixing rates for the horocycle flow in two different ways. And The first method we are going to see is the so-called mixing via shearing method. And has the advantage of being, it's a geometric approach to prove mixing, which has the advantage to be generalizable to other types of parabolic flows, in particular to time changes, as we will do later, in maybe next time. But this method, we will see also as a little problem, namely, the way we are going to apply it will not give us the best mixing rates. And so to see what are the correct mixing rates for the Horocycle flow, I will also mention, or will try to sketch a proof of Ranner's theorem on mixing rates for the Horocycle flow. Okay, but I'll start with this mixing via shearing method. Okay, let me recall once again the setting we are working in. So we look at compact quotient of the group SL2R. Vol is our reference measure, is the Haar measure, normalized to be a probability space. And we look at the Horocycle flow, which is multiplication on the right by this 1 per meter subgroup. And we will also need to use the geodesic flow, as we did last time. So, okay. So what does it mean to be mixing? One way of saying that the flow is mixing means that if you take any measurable set A with positive measure, if you look at the average, say you take an L-infinity function, then if you look at, if you integrate F composed with your flow on A and you divide by the measure of A, so you take the average over A of F composed with HT, this will converge to the integral of F. This is and you can see immediately it's the same as the classical definition of mixing. But I brought in this slightly different way because I want to now not look at the average of the integral of F composed with the flow on a measurable set of positive measure, but I want to look at the same average on some set of zero measure, but quite nice. So I want to, instead of look at measurable sets A of positive measure, I want to replace A by a smooth arc. So I will take gamma to be some smooth curve from an interval, say 0 to sigma into M. And I will say that the smooth arc equidistributes under the flow if I look at the average of F composed with the dynamics on the arc, I converge to the average of the function over the whole space. So, I mean, this is my definition of saying that the arc equidistributes, but it mimics precisely what I see for mixing, right? So the average over the arc pushed by the dynamics, pushed by my flow, will converge to the integral of F. Okay, so what I want to look at this type of statement. What do I choose as my smooth arc? Well, I can choose any short orbit segment of a homogeneous flow that we defined in the first lecture. So at the point P, I can multiply on the right by the exponential of S times W, where W is any matrix in the algebra, non-zero. And I can think of this as a smooth arc of length sigma. And I will take this as my arcs. So the first step is proving that if I can prove that these arcs equidistribute, then the flow is going to be mixing. So I reduce the mixing to a statement about equidistribution of curves. So I want to prove the following lemma. So if I have a function, say in L-infinity with zero integral, and some other function, say in C1, these assumptions are just to make my life easy. I need something, but I just want to make my life easy. Then, if I want to bound the correlation, so if F has zero integral and the flow was mixing, this term would go to zero. So I want to prove that this term goes to zero, and I'm claiming, okay, I can actually bound the correlations of f and g from above with a constant, the C norm of g, and then a term that essentially is a result on is an equidistribution, is an integral of f along the pushed curve gamma w composed with the dynamics up to tentative. Okay, so if I can prove that this term goes to 0, so in here I have the L2 norm, so I would just need to prove that this term goes to 0 for most points, but maybe we want to be ambitious and we want to prove that this term goes to 0 for all points. So if we can prove that this term goes to 0 for all points, then we will have, this would imply mixing. And moreover, these constants are explicit. So if I can prove that this term goes to 0 with some rates, then I will also know that mixing happens at least with some rates. So this is a good way. So we will try to prove that this term for all points p goes to 0, and we'll try to see how fast it goes to 0 when we choose this w appropriately. So again, geometrically, this is along you start from an orbit from a short arc of length sigma, and you push it with the dynamics, and you hope to see something that is equidistributed in the sense that when you integrate f on it, it goes to 0 because the integral of f is 0. I hope this makes sense. Okay, let me prove this lemma. The proof is not very hard in this setting. So the Haar measure is, we proved in the first lecture, is invariant by all homogeneous flows. This is a problem. Well, we didn't prove it, just stated, but it's a property of the Haar measure. So by invariance, I can compose the whole integrand with pi w at time s for any s I want. This is by invariance of the measure. So if this is true for every s, this is going to be true also if I take an average from 0 to capital S and divide by s. So the same statement is still true by taking an average of this quantity, where in the integral now I added this component here, phi w sigma. Okay, and now I integrate by parts. I do an integration by parts. So I take the integral from 0 to s of this quantity here in the middle. And I think of this one as the primitive and this one as the derivative. So when I integrate by parts, I get the integral from 0 to f of the first term times the second term minus the integral of the primitive of this guy, that is going to be the integral from 0 to sigma of the same thing, times the derivative of this term here. And the derivative of this term here, by definition, is the derivative of g along the direction of this flow that I call w. Okay, this is measuring variance and then doing an integration by parts that hopefully I've done correctly. Okay, so if I take this and I plug it back into this equation, I get this maybe not very nice looking formula, but the good thing is that I've written my correlations in a way that contains the terms that I wanted to make up here in the statement. So these terms in brackets are precisely the integral of f along the pushed segment in direction w. Okay, so in this I can apply Cauchy-Schwarz inequality, and so by Cauchy-Schwarz, the first term, so I would need to bound the second term by the L2 norm, but the L2 norm I can bound it by the C1 norm of the function g. I could bound it with L infinity, but okay. And I'm left with 1 over s, the L2 norm of this term in bracket here. And for the second term, again, I would need to bound with the L2 norm of wg, that I will just upper bound it with the C1 norm of g. And so here I have an average over s, so I will just take the sup over all sigma between 0 and capital S of this term in bracket over here. Hopefully this makes sense. I'm being quite brutal with the estimates, but I'm happy with this. And then I just take an upper bound. So here I have twice the C1 norm of G. S, capital S, remember I took it to be less than 1. So I can, so between 1 and 1 over S, the upper bound is going to be 1 over capital S. And the upper bound of these two is going to be the sup of all sigma between 0 and S of this integral over here. Okay, and this proves my lemma. So I reduced my question about mixing to a question about equidistribution of short curves when composed with my dynamics. Okay, so we want to apply this lemma to prove mixing for the Horocycle flow. So the question is, what W do we choose, right? So here, this was true for any W, so for any direction in the algebra, then we make a choice that allows us to prove that this term goes to 0. And the easiest case is look at the case where W is X, X being the direction of the geodesic flow. Okay, why is this easier? Well, we recall that we had a commutation relation between geodesic and Horocycle flow, which is the same as in the picture, in this sketch at the board. So if I start from a point P and I do a Horocycle orbit segment very long of length e to the s times t, so it corresponds to this very long orbit over here, and then I do the geodesic for time s, this is the same as doing first the geodesic for time s, and then doing a much shorter orbit of the Horocycle, orbit segment of the Horocycle flow of length t. Okay? Okay, so this is to close the quadrilateral, but I can think of this in a slightly different way. Okay, this is actually the picture. So if I start from the point P and I do geodesic flow and then Horocycle flow for time t, I land here. That is the same as if I were to flow for time e to the s times t, and then for the geodesic for time s. So if instead of flowing from P for e to the s times t, and get here, if I flow just for time t, which is going to be shorter, I will stop at the 4. So if I start from this whole segment in blue, that is a segment in the geodesic direction, and I compose with the Horocycle flow for time t, what I will see is this curve, this blue curve over here, that if you imagine now s to be very small compared to t, you can think of it as being of the same length in the direction of the geodesic flow, but much longer in the direction of the Horocycle flow. Does the picture make sense? Right, so if t is very large, well, this is much larger than this, so this point is far behind. So, and it's similar for points in the middle, so you will have this long orbit. And this is the shearing effect in the mixing bias shearing. So if you look at these transfer curves and you push with the Horocycle flow, they stayed of the same length in the direction you took, but they become sheared in the direction of your flow. Okay, so let us do this. So gamma x of P and sigma is going to be a segment of geodesic orbit starting of P of length sigma in x direction of the geodesic. And sigma is going to be less than 1. We'll choose it later, but for the moment, less than 1. Okay, so again, if I do my commutation relations that I did before, well, I get that the segment pushed with the Horocycle flow is going to be phi of x composed with the Horocycle flow at time e to the s times t. And now if I think of s to be, if I think of sigma being very small, this is not very far from h of e to the s times s of t. So in the picture corresponds to say, okay, if this is not too big, then this curve is just going to be something parallel to this arc over here. Okay, so this arc over here. So if I want to be a bit more precise, maybe I can say, okay, if I want to look at the integral of f along my pushed geodesic segment, what would be the error that I commit if I replace it with the integral along this arc over here? Well, it would be the integral of this difference over here. And then if I apply the mean value theorem, is my function is in C1. this is going to be bounded by the norm of the derivative of f in the direction of the geodesic times the length of the distance of these 2 points, that is going to be sigma, integrated from 0 to sigma. So I get another sigma square over here. Does this make sense? Okay, so this is the quantity I wanted to study, and I wanted to prove that this integral will go to 0. And the first reduction is replace it with this term over here. And this is going to be the integral of f along the support of Horocycle orbits, but the parametrization is a different one. So we need to work on this parametrization for a bit. Well, in this case, it's not too hard because e to the s, I can write it as 1 plus s squared over 2, blah, blah, blah. And if I truncate my expansion up to the second term, so the error I commit is going to be of order s squared times t. So if I replace now this integral over here with the integral of f composed with h of s plus 1 times t, then again, the error I commit by the mean value theorem is going to be the norm of the derivative of u in this direction of h, which is the derivative in the Horocycle direction, times something that is of order s squared that is going to bind with sigma squared, and there is an extra integral from 0 to sigma, so I get sigma cube times t. Does this make sense? Okay, so I'm working my way to reduce the integral along this curve with the integral along the Horocycle orbit segment. This is what the picture was suggesting. So this is what we're trying to do. Okay, so from this integral, we reduce to this integral over here, up to an error that is the sum of these two errors. And from here, I can do a change of variables, because this is an integral in S. So this is an integral that starts from ht of p. And the integral is s times t, but I can do a change of variables, replacing s times t with a new variable. And this thing will become this average. So this is a 1 over t times the integral from 0 to sigma t of f composed with hs. So now this time I have a good parametrization of the Horocycle along the Horocycle orbits, starting at the point ht of p. Okay? So I don't know if I'll say it once more, just to be sure. So the integral along this blue segment pushed with the Horocycle story is going to be this segment. So what we did was, instead of this segment, first look at this segment over here. So it was parameterized different, and we did some reduction to change the parametrization into integral starting from ht of p up to here with the natural parametrization of the Horocycle orbits. This is what we did up to here. So to sum up, the integral that we needed to compute minus this, that is our the thing that we want to study, can be bounded by this error that was of order sigma square plus sigma cube times t. And what we are left is this object here, which is essentially an ergodic integral along the Horocycle flow, starting at this point. But in the last lecture, we managed to bound this type of integrals for all points. So we can use actually the
Yes, but on the right-hand side, you still have t, which is
right
against.
Right. So I will be.
Then you will.
I will choose sigma to be so that this thing is going to be small. You see, there is a bit of a game because you want sigma times t to be large because you want this integral to be large, but you don't want it. But at the same time, you want sigma cube times t to be small. So there is a bit of a trade-off to play.
It's a disaster. It's not a disaster.
It's not a disaster, yes. All right, so in the last lecture, we proved that the integrals of this form, when f has a zero average and is sufficiently smooth, they can be bounded. So the error we committed was a polynomial. I mean, we had a whole series, but if we truncate to the first term, we get a polynomial upper bound on the error. And the polynomial is the extreme of integration, sigma t, to some power that with an explicit power. So at the moment, I don't really care what, I would care what the power is, but say for the moment it's just sigma times t to some power. And this is true, I mean, this power is explicit whenever sigma times t is greater than 1. Okay, so what did we prove?
So
Sure.
this U0 is related to some spectral.
Correct. So this nu0 is related to the smallest positive eigenvalue of the Casimir or the Laplacian. Okay, so it's okay, so what did we prove? In any case, it's a constant that depends only on the geometry of the space you are in. So what did we prove? We proved that this integral that we needed to bound can be bounded by some constants that depend on my space, the C4 normal f times a term that depends. So this is what comes from this integral. So there was a 1 over t in the previous, so t to the minus 1 times the minimum of this bound here and the trivial bound, which is just sigma times t. Okay, and the error we committed in the previous the reductions that we did. And now we choose sigma to make this guy as small as we can. And if I choose sigma, for example, to be t to the minus 1 over the square root of t, then all this term over here, I can bound it by some 3 minus nu naught over 4, some positive, well, some negative exponent here. So now if I apply my mixing via shearing lemma, what is this telling me? Okay, if I apply the mixing via shearing lemma by choosing the total length of my segment to be 1 over square root of t, then we just proved that for any C4 function, okay, which has 0 average, and for any g, which is C1, then the correlations can be bounded above by some constant. Well, the mixing via shearing lemma was telling me that this was bounded by the C1 normal g times 1 over capital S, so t to the square root of t, times this term, the sup of this term over here, that we bounded by reducing them to an ergodic integral for Horocycle flow. So by plugging in the estimate that we proved before, and let me stress that the estimate we proved here is true for every point. Okay, so here we just would need the L2 upper bound, but we managed to prove it for every point, so it's a stronger result. Anyway, if we plug those estimates into here, we managed to prove that these correlations are bounded by some constant, some term that depends on the norm of f and g, and the negative power of t, that we can make explicit in this case. So what did we manage to prove? Well, we managed to prove that the Horocycle flow is mixing. This term goes to 0. And moreover, we managed to prove that mixing happens with at least polynomial rates. So if I compute the correlations minus the expected values, well, this will decay polynomially in t. And we actually found a bound for the exponent appearing in the decay rate. Does this make sense? So again, by using the mixing via shearing lemma, so look at short curves that are transverse to your flow and see what happens when you push them with the dynamics. We managed to prove that the Horocycle flow is mixing, and we managed to prove that it's mixing with polynomial rates. Okay, so the natural question is, what is this rate? Then we say exactly what is the mixing rate. Maybe it's faster than what we proved. So what is the optimal exponent? Okay, so the mixing via shearing lemma that was was bounding the correlation with these integrals along these pushed curves was telling us that the speed of mixing is bounded by the equidistribution of these curves. And in the statement of the lemma, we have complete freedom in choosing the directions we want to push. Then what we did is choosing geodesic arcs. And we managed to prove that if we push the geodesic arcs with the Horocycle flow, they become equidistributed because they approximate an orbit segment of the horocycle flow of length sigma times t. If you take a geodesic segment of length sigma and you push for time t, you get something that looks like, if you look for sufficiently far, it looks like a horocycle orbit segment of length sigma times t. So if I apply this strategy and I want to ask myself what is the rate of mixing for the horocycle flow, okay, sorry. These approximate a horocycle orbit segment of length t times sigma, and since we proved that they are these equidistribute, this pushed segment becomes equidistributed at t goes to infinity. And the rate of mixing we can prove following this strategy over here, well, even if we ignore all the errors we committed by doing our approximation, it's definitely not going to be better than the speed of equidistribution of horocycle orbits. Right, we made some error in sigma, and then we needed to choose sigma to make the error not too large. But even if I were very optimistic and I managed to take, say, sigma equal to 1 and ignore all the errors in sigma, we couldn't. We had to choose sigma sufficiently small. But to say that I managed to take sigma equal to 1 and all the errors are not there, and this will be an horocycle orbit segment of length t, then the speed of mixing I get is definitely at best the speed of equidistribution of the horocycle flow. But maybe this is not the best. Maybe some other curves equidistribute faster than geodesic segments. And indeed I want to tell you that this is the case. So I want to talk briefly about equidistribution of other curves, mainly because hopefully it's motivated by this question of what is the optimal speed of mixing for horocycle flow, but I think it's a result that is interesting in its own right. And so the spoiler is that yes, other curves become equidistribute faster, and in hindsight, perhaps it's not very surprising, because what happens for geodesic and horocycle flow, so the space M is three-dimensional. The group SL2R is 3 dimensions. And what happens for geodesic and horocycle flow stays in a 2-dimensional leaves. The X and U directions are integrable, they form a foliation. So if you push geodesic with horocycle, okay, they will equidistribute, but it will leave, the pushed curve will live in the same leaf of horocycle. So maybe it's not too surprising that if you pick something transverse to that leaf, it might equidistribute faster, because it's not, it doesn't have to live on a 2-dimensional object inside a 3-dimensional one. Anyway, so if I have 10 more minutes, I want to say something about equidistribution of other curves. So it's a result by Buffetto and Forni that if you, well, it's a consequence of a result by Buffetto and Forni, that if you ask, so take a direction. So before we took only the geodesic, now I say, okay, take any direction that is a linear combination of horocycle and geodesic. So anyway, it's going to be something that lives on this 2-dimensional immersed submanifold. So if I ask myself how fast do they equidistribute when I push them with the horocycle flow, well, you can, as U is the direction of the horocycle.
But the same horocycle as defined by H, or?
Yes. Yeah, so you can ignore this term. It's just a thing.
Okay.
So if B is equal to 0, this will never equidistribute.
Sorry?
If B is equal to 0, this will never equidistribute, because I'm pushing a segment by the flow itself.
Yeah, but it does not seem to be a good candidate. So if we come back to your explanation about 2-dimensional foliation, so
yes.
It's rather wrong direction.
Yes. I just wanted to say that what we saw for the geodesic flow happens for all vectors in this 2-dimensional subspace. So if I take a vector that is linear combination of geodesic and horocycle, so it lives in this 2-dimensional object, then if I want to look at how fast the pushed curve in that direction equidistributes, well, this is going to equidistribute at the same speed as horocycle orbits do. So for any S, there exists some constant such that for all sufficiently smooth functions with zero average, and for all points, the equidistribution of the pushed arc with the horocycle flow is going to be bounded by a constant times the norm of F times a negative power of T, and this power was the same as for the horocycle orbit segment, up to a logarithmic error. I will ignore logarithmic errors for the moment. Okay, so this is what we actually were discussing before. So the question is, what happens if we take some direction that is not in this two-dimensional subspace, transverse to this? And well, I proved it. I mean, it's in the end it's a consequence of Buffetto and Forni, but it needs you need to make a geometric observation that I will tell you about. So if now I take a direction that is not parallel to U and X, but it has a non-zero component in the direction of in the other directions, in the direction of the unstable horocycle flow. Then what happens is that the equidistribution happens at a rate that is twice as fast as the rate of equidistribution of horocycle orbits. So I don't know, perhaps it's at least at first it's not entirely clear why, but I will show you it boils down to a observation. But so segments that are transverse to the stable and geodesic directions equidistribute twice as fast when you push them with the horocycle. So if I were to repeat my argument for equidistribution of segments and hence mixing for horocycle flow, I would get a much better exponent in the mixing rate by using the mixing by Oshiri lemma, not with geodesic arcs, but with any arc of this form. I will get a mixing rate that is twice as fast, like twice that. All right, so this is what I was saying in words. So arcs transverse to this foliation equidistribute twice as fast, and so the mixing rate of the horocycle flow is at least this exponent over here, and we will see later that indeed this is the optimal one by proving Ratner's theorem. And I don't think I have time left.
So formally, you have 2 minutes, but if you
2 minutes,
or be our guest.
Okay, stop me if I go to. I want just to give an idea of why this is the equidistribution of these segments is faster. I will not prove the statement in this form. I just want to hint what's the geometric observation that allows you to deduce this result. And if you've never seen, I think it's quite nice. So let me look at the case where I take an unstable horocycle segment. So a segment in this direction here, where I multiply by 1, 0, S1 for some S in 0, 1. And the key geometric observation is the following. So if I take this matrix over here, and now I push with the horocycle flow for time t, and now I push again with the same unstable horocycle flow for a time -1/t. So I'm taking a unstable horocycle segment, pushing for the horocycle flow for time t, and then changing a little bit in the unstable direction for times -1/t. I get exactly horocycle flow time t, unstable horocycle -1/t, and then this matrix over here. So this is a product, so you can verify it's just a product of metrics, but geometrically it's telling me something that I find quite surprising and quite interesting. If I take a segment of length sigma in the unstable horocycle direction, and then I push it with the horocycle flow for time t, and then I push it by very little, because imagine t is very large, so this is going to be very, very little in the unstable horocycle direction. This is going to be the point P composed with this matrix, composed with the matrix. It's going to be some different point PT. don't really care what this point T is, but it's going to be this T times these two matrices, composed with H at minus ST squared. So this is what we proved. So imagine now that T is very large, so that this term is very, very little, and maybe I can forget about it. So what is this telling me? So if I forget about this term, it's telling me if I take an unstable Horocycle segment and I push for the stable Horocycle for time t, and I do an average over this segment, roughly, so if I neglect this term over here, I get an average over H composed with minus ST squared at some point P. And now if I do a change of variables, to call this my new variable, so what this is telling me is that a short unstable Horocycle pushed with Horocycle time t looks very much like an orbit of the Horocycle flow in the negative direction of length t squared. And this is why the equidistribution happens twice as fast, because if you push it for time t, you get an Horocycle orbit of length t squared. And this is where the square.
Finally, you use the same quantitative equidistribution result for the Horocycle flow.
Yes. Yes. So because if I were to just do a simple-minded approximation by this, I would commit an error that I don't like. So I use the equidistribution of not quite Horocycle orbits exactly, but almost Horocycle orbits. Yeah. I use Buffetto and Forni's result because they have an equidistribution for Horocycle-like segments, not because I could just do an approximation, but I would lose some exponent that I don't like. So by using the result, you still reduce it to equidistribution of something that looks very much like a Horocycle orbit segment of length t squared, and so you get the twice.
And probably this logarithm is a cost of.
The logarithm actually comes from the fact that this result of Buffetto and Forni is defined only for positive eigenvalues of the Casimir. And for negative eigenvalues, I have to go by hand, and I commit an error of size 30.
Okay, so it's something different.
Yeah, I don't know if it's just that I couldn't use exactly the results. By going by hand, I was losing a log t in the. All right. And okay, so at least we convince ourselves that okay, these curves equidistribute faster, so the speed of mixing for the Horocycle flow is at least the one coming from equidistribution of these curves. And so next time I want to talk about Radner's theorems, that is much earlier than these results, sorry. And she proved the optimal mixing rates for the Horocycle flow, and I want to sketch her proof. And but for the moment, I'll stop here.
Next time it means today.
Yes.
Okay, questions, comments? If we don't have, so thanks again. And coffee break. It's later.